What if I told you that one of the biggest breakthroughs in modern AI wasn't some super complex, intimidating algorithm, but actually a surprisingly simple, almost counterintuitive trick? Well, that's exactly what we're talking about today. We're diving into Dropout, the clever idea that really helped unleash the power of deep learning. So let's start with a kind of weird question. Can a machine actually be too smart? And in the world of machine learning, the answer is a resounding yes. You see, when a model gets too good at learning the specific data you trained it on, it ends up just memorizing it. It knows the answers to the test, but it hasn't actually learned the subject. And that is a huge, huge problem. All right, so here's our game plan. We'll start by really digging into this overfitting problem. Then we'll introduce the clever, simple idea of dropout. We'll look at how it actually works, check out its incredible winning record, and then finish up with some pretty stunning visual proof of why it's so effective. Okay, let's get into it. First up, we need to meet the villain of our story, the overfitting problem. This is exactly what happens when a model's incredible intelligence becomes its own worst enemy. So what is overfitting? The best analogy is a student who's cramming for a big exam. They don't learn the concepts, they just memorize the exact answers to the practice questions. Now, they might totally ace that practice test, right? But the moment the real exam throws them a new question, even one testing the exact same idea, they're toast. They're completely lost. That's what a model does. It learns the noise and the quirks, not the actual signal. And here's the real kicker. Deep neural networks are so amazing because they can learn these incredibly complex, subtle patterns in data. But that very same power, that incredible ability to learn, makes them especially good at just memorizing the noise. So their greatest strength is also their greatest weakness. So how in the world do you fight that? Well, not with more complexity. It turns out the answer was a brilliantly simple idea, and it was inspired by some pretty wild places, from evolution to, believe it or not, conspiracies. Here it is, the whole idea in a nutshell. While you're training the network, for every single piece of data you show it, you just randomly turn off or drop a bunch of its neurons and their connections. That's it. You're basically forcing it to do its job with a slightly different, slightly handicapped version of itself every single time. The authors of the original paper had this fantastic analogy. Let's say you want to cause some trouble. One giant conspiracy with 50 people is actually pretty fragile, right? If just one person slips up, the whole thing can fall apart. But 10 smaller, independent conspiracies of 5 people, now that is way more robust. And Dropout works just like that. It prevents the network from forming one big, fragile conspiracy of neurons that all depend on each other. And they also looked to biology for inspiration. Think about sexual reproduction. It's constantly shuffling genes, breaking up these comfortable little sets of genes that have gotten used to working together. This forces every single gene to be useful on its own, because it has to be ready to work with a whole new random set of partners in the next generation. Dropout does the same thing to neurons. It forces each one to be useful by itself, because it can't rely on its specific neighbors being there to back it up. And this table just lays it all out perfectly. In a standard network, neurons can get, well, kind of lazy. They form these codependent little cliques. But with a dropout net, any neighbor could vanish at any moment. So every single neuron has to be more robust, more independent. And that makes the whole network way better at handling new data it's never seen before. Now, I know what you're thinking. This whole randomly dropping things sounds, well, chaotic. But it's actually incredibly controlled. All that chaos is just for the training phase. When it comes time to actually use the network to make predictions, something really, really elegant happens. So here's how it goes during training. For every single data point, let's say an image, you show the model, you first create a new thin version of the network by randomly dropping out some neurons. Then you do just one little step of training on that smaller network. And you just repeat this over and over again. You're effectively training this enormous collection of different networks that all happen to share the same weights. The real genius is this contrast between training and testing. Training is total chaos, right? You're sampling from potentially billions of these thinned-out networks. But at test time, it's all order. You use the full, complete network with all the neurons. And here's the magic trick. You just scale down the network's weights. That one simple step mathematically approximates the result of averaging the predictions from all those billions of smaller networks you trained. It's an unbelievably efficient way to get the power of a massive model ensemble without the cost. Okay, the theory is cool, the analogies are great, but did it actually work? Oh boy, did it ever. The results speak for themselves. Dropout didn't just give a small boost, it completely smashed records all over the place. Let's start with MNST. This is the classic hello world of computer vision, recognizing handwritten digits. A standard network back then got about 1.6% error. Just by adding Dropout, that number goes down. But when you combine it with some other techniques and fine-tune with Dropout, the model achieved a new state-of-the-art result of 0.79% error. I mean, that's a huge improvement. Okay, MIST is great, but it's pretty clean. What happens when you throw a really messy real-world problem at it? Well, this is the Street View house numbers dataset. And as you can see, these images are just a mess. They're noisy, they're cropped weirdly, there's all kinds of visual clutter. This is a much, much tougher challenge. And the result? Just look at that. Dropout slashed the error rate by a staggering 35%. The original network had an error of about 3.95%. Adding Dropout dropped that all the way to 2.55%. That is a massive leap in performance on a really hard task. But this is the one that really changed everything. This is the result that kicked off the modern AI revolution. At the big ImageNet competition in 2012, the best traditional computer vision methods were all stuck around 26% error. Then a new deep convolutional neural network, with Dropout as a critical component, showed up and got around 16% error. People's jaws were on the floor. This wasn't just an improvement, it was a completely different league. And this is so fascinating because it shows you what those numbers really mean. Take a look at that third image. The correct answer is morel, the mushroom. The model's top guess was stinkhorn, which is wrong, but hey, it's another type of fungus. And look at its other guesses. They're all mushrooms. The model isn't just seeing pixels, it's learning concepts. It actually understands what a mushroom looks like. So we've seen the incredible results, but let's wrap this up by actually looking under the hood. We can peek inside the network and see the profound effect that Dropout has on what the neurons themselves are actually learning. So remember the core idea. By making its neighbors unreliable, Dropout forces every single neuron to pull its own weight. It has to learn to spot features that are genuinely useful all by themselves. Okay, this slide right here is the aha moment. On the left, you see the kinds of features learned by a standard network. They're kind of noisy, a bit fuzzy. It's hard to tell what any one neuron is even looking for. Now, look at the right. With Dropout, the features are so clean and crisp, they've become these beautiful independent detectors for things like edges and strokes and spots. These are way more useful, robust building blocks for understanding an image. And check this out. There's another amazing side effect. These graphs show how active the neurons are. On the right, with Dropout, you see that massive spike right at 0. What that means is, for any given image, most of the neurons are just silent. The network has learned to be sparse and incredibly efficient. It only activates the few highly specialized neurons it really needs to get the job done. So in the end, Dropout is so much more than just a clever programming trick. It's this powerful proof that sometimes the best way to build a strong, robust system isn't to add more complexity, but to inject a little bit of strategic chaos. And that leaves us with one final thought to chew on. What other really complex problems, whether in AI or somewhere else entirely, could be made stronger just by embracing a little bit of randomness?